In this video, we shall define a class of functions that arise as the increasing limit of step functions, and we will also define how to define the integral of such functions. To begin with, we need a simple lemma. This talks about the behavior of the limit of an increasing sequence of functions. Let Tn be an increasing sequence of step functions, such that Tn increases to a function f almost everywhere on the interval I. So these Tn's are from I to R. Okay. Further assume that integral of Tn over I converges. Then if T from I to R is any step function such that T is less than or equal to f almost everywhere on I, then integral of T is less than limit n going to infinity of integral of Tn. So this is a somewhat technical sounding lemma, but this will be the basis for the definition of the integral of the upper functions. What it is essentially trying to say is the following. If you have a sequence of step functions that increase to a given function, then no step function that is less than or equal to the limit function can have a greater integral. That's essentially what this is saying. As you can guess, we are going to define the integral of the function f using this formula. And this fact that integral of t over I is less than or equal to limit n going to infinity integral of I Tn will sort of help us to prove the well-definedness of the integral of the function f. So let's see the proof. The lemma looks technical, the proof is rather trivial. It just follows immediately from the previous theorem that says that if you have a sequence of step functions that decrease almost everywhere to a function to 0, then the integrals also converge to 0. Now what we are going to do is we are not in the situation of the previous theorem. The previous theorem had a decreasing sequence of step functions. So we manufacture a decreasing sequence of step functions using this sequence of step functions Tn. So what we do is we define Snx by definition to be equal to T of x minus Tnx if T of x is greater than or equal to Tnx. Remember, t is some step function that is less than or equal to f. 0 otherwise. So in more fancier notation, Snx is just the maximum of T of x minus Tnx and 0. Okay. Now observe that Tn increases to f almost everywhere and T of x is less than or equal to f of x almost everywhere. Combining both, it follows from, let's call this star, it follows from star that Sn decreases almost everywhere to 0. Okay. Since Tn's are an increasing sequence of functions, it's clear that Sn's are decreasing, and furthermore they must decrease to 0 because Tn's converge almost everywhere to f. So at some point of time Tn has to become greater than t because t is less than or equal to f. So this first term has to become less than or equal to 0 after a point, in which case this maximum will become 0. So from the previous theorem, integral of Sn over I converges to 0. Now because Sn of x is greater than or equal to t of x minus Tn of x, because it's the maximum of this quantity comma 0, using the various properties of step integrals of step functions, we get integral over I Sn of x is greater than or equal to integral over I t of x minus integral over I Tnx. Right? Now let n go to infinity, so we get limit integral over I Sn of x n going to infinity, which is just 0, and this is greater than or equal to integral over I t of x minus integral over I Tn of x limit n going to infinity. In other words, we get integral over I of t is less than or equal to integral over I Tn limit n going to infinity as claimed. With this basic lemma in hand, we can now define upper functions, which is going to be a class of functions, and we can define the integral for upper functions. So the definition is as follows. A real valued function f from I to r, where I is some general interval, is called an upper function if we can find an increasing sequence of step functions Sn such that Sn increases to f almost everywhere and limit n going to infinity integral over I Sn is finite. Okay. If you can find a sequence of increasing functions which increase almost everywhere to f, then we say f is an upper function. The collection of upper functions is denoted u of I. The sequence Sn is said to generate f. That is, for a sequence of step functions to generate f, first of all it must be increasing, second of all it must increase almost everywhere to f, third point the integral should the limit of the integral should be finite. We define integral of f over I by definition to be the limit, as hinted before several times. Okay. Now notice that this sequence integral of I Sn, because Sn's are increasing because of the property of integrals of step functions, this sequence integral I Sn is also an increasing sequence. So for this limit to exist, it's actually enough to assume that this sequence of integrals is actually bounded above. That's another equivalent way of stating the same thing. Now the crucial part is there could be several sequences of step functions that generate f. What is the guarantee that all of them lead to the same value of integral of f over I? Essentially, what is the guarantee that this collection of functions u of I, the integral defined on this collection, why is it well defined? Well, that's the content of the next theorem. So this theorem says well definedness of the integral integral. So let f be an upper function and let Sn comma Tn from I to R generate f. Then integral of Sn limit n going to infinity is equal to limit n going to infinity integral of Tn. Okay. Now observe the following. This proof is rather an easy consequence of the previous lemma. So observe that each Tn is less than or equal to f almost everywhere. So if you look at the previous lemma, it says that if you have a step function t which is less than or equal to f almost everywhere, and the sequence of functions tn increase almost everywhere to f, then integral of that t is less than limit n going to infinity of tn, integral tn. So what that shows, the previous lemma immediately gives us, previous lemma gives integral of Tn I is less than or equal to limit n going to infinity of integral of Isn. Okay, and you can just pass to the limit on the left hand side also. So we get that limit n going to infinity integral of Itn is less than or equal to limit n going to infinity integral of Isn. By symmetry, we get the opposite inequality. Same argument. We get the opposite inequality. We are done. So the well-definedness of the integral is very easy to show from the lemma, and ultimately that lemma was a consequence of the behavior of decreasing sequences of step functions. So ultimately everything hinges on the theorem that we did in the previous video. Okay, now let's state some simple properties of this upper integral, and we will, in the next few videos, we will extend this definition to a larger class. And this next theorem sort of highlights the problem with this particular collection of functions. It's not really a vector space, which is sort of not nice. Let f be an upper function. And g also an upper function. Then number 1, f plus g is an upper function, and integral of f plus g over I is just integral of if plus integral of ig. Number 2, here is the problem. If c is greater than 0, then cf is an upper function, and integral of cf over I is c times integral f. So here we actually require c greater than or equal to 0. There are upper functions whose negative is not an upper function, and this is sort of problematic. And not nice. There are explicit examples. You can check Apostle's exercises where there's an explicit example listed. Property 3, if f is less than or equal to g almost everywhere on I, then integral over if is less than or equal to integral over ig. Okay, so parts 1 and 2 follow from definitions. There's really nothing to prove. Follow from definitions. Okay, and I want you to prove 2 in particular. 1 is pretty much trivial. I want you to prove 2 in some detail and see where the proof breaks down if c is less than 0. That's a very instructive exercise. Let's move on to the proof of part 3. Let Sn be a sequence of step functions that generate f, and let Tn be a sequence of step functions that generate g. Now the hypothesis is that f is less than or equal to g almost everywhere on the interval I. Okay, that means Sm of x is less than or equal to f of x is less than or equal to g of x, which is nothing but limit n going to infinity of Tn of x, and these inequalities and equalities are true almost everywhere. Okay, now that means from the previous theorem that we had, the big theorem about what happens if a step function, sequence of step functions converge to a function f, if you take any other step function that is lesser than or equal to that function, then we definitely have integral over I of Sm is less than or equal to limit n going to infinity integral over I Tn, which is equal to integral over Ig. This just follows from the big theorem which we proved in the last video. Now taking limits on the left hand side, taking m going to infinity, we get integral over I f is less than or equal to integral over Ig. So this was a fairly straightforward proof. An easy corollary of this is something that you might have anticipated already. Let f comma g be upper functions on the interval I, and suppose f is equal to g almost everywhere. Then integral of if is integral of Ig. And this follows immediately by observing that f equal to g almost everywhere is the same as saying f less than or equal to g almost everywhere and g less than or equal to f almost everywhere, and applying the previous result. So we have now shown one nice property of the Lebesgue integral. For the Riemann integral, we know that a necessary and sufficient condition for the existence of the Riemann integral is the set of discontinuities being a set of measure 0. But you can take a function and modify it on a set of measure 0 to make it discontinuous everywhere. Please think about the remark I said carefully. What will happen is you can start with a continuous function and just modify it on a really small set to not make it Riemann integrable. That's not something that you want from an elegant theory of integration. Here, in the case of Lebesgue integral, which we are going to eventually define, at least for upper functions, if you have two upper functions that agree almost everywhere, then their integrals are actually equal, which is what we sort of expect because these two functions are the same except on a negligible set. Okay, so the last few properties that I want to prove for the integral on upper functions is about their property when you break up the interval. For that, the following technical looking thing is useful. So let me call it a lemma, which is going to be used in the next theorem about breaking up the intervals. The lemma is as follows. Let f comma g be upper functions, then both max fg as well as minimum fg are also upper functions. And again, the proof of this is rather straightforward. Pretty much everything I have done except for the proof of that theorem about monotone sequences where a little bit of analysis was actually involved. Pretty much everything is just a straightforward corollary of that theorem and the various definitions that we have. So what we do is let Sn generate f and let Tn generate g. This is sort of the standard first line boilerplate for every single lemma. Now we want a sequence that generates max fg and min fg, and you can easily check that max of Sn Tn is a sequence of step functions that generate f. Let's just call this sequence un, and similarly vn equal to minimum of Sn Tn generate g. Now actually I shouldn't technically be using the fact that, I should not technically say generate f. So to be 100% precise, what we will do is we will consider un equal to max Sn comma Tn and Vn equal to min Sn comma Tn. All we can assert is un increases to max Fg almost everywhere and Vn increases to min Fg almost everywhere. Remember, when you say that a sequence generates a given upper function, you will have to first of all show that the integrals, the limit of the integrals converge. Only then is actually the limit function even an upper function in the first place. So we know that both un and vn increase to max Fg. So what we have to show is integral of I un and integral of I vn exist. And as I have remarked earlier, actually the limits, limit n going to infinity of both of this exist. As I have remarked earlier, because vn's are increasing, this is actually going to be an increasing sequence, the integral over I vn. So it suffices to prove that this sequence is actually bounded above. And it's rather easy to see that this sequence is bounded above simply because vn is less than or equal to f almost everywhere, right? And this just follows because vn is defined to be minimum of Sn comma Tn and Sn is less than or equal to f almost everywhere. So because vn is less than or equal to f, it follows that integral of I vn is less than or equal to integral of if. This is by part 3 of the previous theorem. This shows that integral of I vn, this sequence, this set is bounded above. So that shows that minimum of Fg is an upper function. Okay. Now, how do you show that max of Fg is an upper function? You can't pull the same trick because you don't have un is less than or equal to f for obvious reasons. So what you do is you try to be slightly clever. You observe that maximum of this Sn comma Tn is actually just Sn plus Tn minus Vn. Okay. In other words, finding out the maximum of the two quantities is same as summing up the two quantities and subtracting the lesser of the two quantities. Intuitively obvious. And that's what we have used here. So un is Sn plus Tn minus Vn. Therefore, by the algebraic properties of the integrals for step functions, note these are all step functions. I already remarked that when you have a function f, it is not guaranteed that the negative of the function is an upper function. You can write this simply because these are all step functions. Integral of I un is integral of I Sn plus integral of I Tn minus integral of I Vn. Okay. And as limit n goes to infinity, this is just integral of I un, limit n going to infinity of this is just integral of if plus integral of ig plus integral of I, not plus, minus integral of I minimum of fg. And that finishes the proof. We have already shown that this integral exists and therefore we are done. So we are done. So this somewhat technical looking lemma we are going to use to show that you can split the interval of definition of an upper integral, upper function and evaluate the integral by breaking up the intervals. So let's state the theorem. Let f be an upper function on the interval I. Suppose suppose I'm going to state it for just two intervals. You can use induction and prove the same thing for finitely many integrals. Suppose I is I1 union I2, where I1 and I2 are intervals with no interior point in common, or intervals with no interior point in common. Interior point in common. Then integral of IF is just integral of integral of I1F plus integral of I2F. So you can split the definition, the domain of definition, into two intervals, and then you can evaluate by evaluating the integral on the two pieces separately. Similarly, suppose f1 is an upper function on I1 and f2 is an upper function on I2, and we define the new function g to be f1 of x if x is in I1 and f2 of x if x is in I2. Technically this definition is not exactly precise, because it can happen that there is an endpoint in common between I1 and I2, with the understanding that we define f to be some value at the g to be some value at I1 intersection I2. It really doesn't matter whatever value you put. You can choose your favorite real number and put f to be that in that place. One second, I think I missed one crucial hypothesis. I actually require f is in upper function and f is greater than or equal to 0 almost everywhere. You will understand why I am going to put this hypothesis, why I need to put this hypothesis here in the proof. For this it doesn't matter. For this second part it really doesn't matter. F1 and F2 could be any upper functions whatsoever. Then g is in u of I, and integral of ig is just integral of I1 F1 plus integral of I2 F2. Okay, so this second part I'm going to leave it to you. It's fairly easy. Let's deal with the first part and see where that extra hypothesis that you need f greater than or equal to 0 almost everywhere, where is that used. So let's go on to the proof. So let Sn generate f. Now I want to use this Sn to generate a sequence of positive step functions. So what I do is I look at max of Sn comma 0 and I call that Sn plus. Okay, because f is greater than or equal to 0 almost everywhere, we have Sn plus also generate f. Okay, here is the crucial part where I required that f is greater than or equal to 0 almost everywhere. The fact that Sn pluses are increasing is obvious because Sn is increasing, but the fact that Sn plus increases to f almost everywhere requires f to be greater than or equal to 0. Okay, now note that integral of I1 of Sn plus is obviously less than or equal to integral of I Sn plus, which is in turn less than or equal to integral over IF. Okay, which means Sn plus generates f restricted to I1. So for this inequality, that integral of I Sn plus is less than or equal to integral of I Sn plus, I require the positivity of the functions. what is essentially happening is I is a larger interval, but since the values of Sn plus are non-negative, this integral can only increase and not decrease. So this is the crucial place that actually hinges upon the positivity, or rather the non-negativity of the original function f. So Sn plus generates f restricted to Sn plus restricted to I1 generates f restricted to I1. Similarly, Sn plus restricted to I2 generates f restricted to I2. Now it's obvious that for step functions we have this. When you break up the interval of integration for a step function, you get this obvious equality. Integral of I Sn plus is just integral of I1 Sn plus integral of I2 Sn plus. And when you take limits, you get integral of IF is equal to integral of I1 f restricted to I1 plus integral of I2 f restricted to I2. Okay, so this completes the proof. So more or less all the basic properties of the Riemann integral are also enjoyed by this integral on upper functions. As a next step, we are going to show in the next video that any Riemann integrable function is automatically an upper function, and the Riemann integral coincides with the integral we have defined for upper functions. Once we are done with that, we can move on to the definition of the Lebesgue integral. This is a course on real analysis, and you have just watched the video on upper functions and their integrals.